So we want to perform the indicated operation and write each expression in simplest form. So number 1, 3 divided by a plus 2 plus 4 divided by a minus 5. When we add fractions, which means when we add rational expressions, we need a common denominator. We need a common denominator to add and subtract rational expressions. So the first denominator has a factor of x plus 2. The second denominator has a factor of a minus 5. So that first expression needs a factor of a minus 5. Well, how do I add an a minus 5 into that denominator? Well, I also need to multiply the numerator by a minus 5 because this number here is actually just 1. That a minus 5 divided by a minus 5, we have to remember, is just 1. A minus 5 for the second term is in the denominator already, so I need a factor of a plus 2. So I can put a factor of a plus 2 in the denominator, but I also need it in the numerator, because again, I can only multiply an expression by 1 without changing its value. That's one of the rules of mathematics, is I can multiply it by 1, I'm not going to change its value. So in the top over here, I get 3 a minus 5 plus 4 times a plus 2, and they're both over a minus 5 times a plus 2 times a minus 5 times a plus 2. Now that they have a common denominator, these expressions are all equivalent, I can write it as one single fraction, and I'm going to distribute here. 3a minus 15 plus 4a plus 8, all divided by the common denominator, a minus 5 times a plus 2. Do not start distributing stuff out. Don't start distributing that denominator, because maybe I can have a factor in the numerator that I'll cancel out. I don't know yet if that's going to happen, but it could. So 3a and 4a gives me 7a, minus 15 plus 8 is negative 7, divided by a minus 5 times a plus 2. Notice that I have a GCF of 7 in the numerator, so I'm going to want to factor that out. And this leaves me with my final expression. This expression is equivalent to that original expression that we started with. Things to notice: I don't have to expand the denominator back out because that would just be wasting time. Also remember, from the first day of this unit, we said that a cannot be 5 and a cannot be negative 2, because otherwise I'd be dividing by 0. That's just something to always keep in mind. With rational expressions, your denominator cannot be equal to 0. Number 2, find the sum here. So to add, I need a common denominator. N squared minus 25, I notice that as n plus 5 and n minus 5, plus 3n divided by 5 minus n. Now, it would be really nice if that 5 minus n was an n minus 5. And luckily it is. Luckily it is, I just have to factor out a negative 1. I have to factor out a negative 1 and use the commutative property, and 5 minus n is equivalent to negative 1 times n minus 5. Which will make my common denominator, working with the common denominator, much easier. I'm going to take that negative 1 and put it in the numerator, because I can do that. And now, this becomes a much easier question to tackle. Because the common denominator, I need a factor of n plus 5 and a factor of n minus 5. So I'm going to have to multiply that first rational expression by a factor of n plus 5. That way I'll have a common denominator. Notice I'm multiplying both the numerator and the denominator by n plus 5. The second rational expression already has the common denominator, so I don't need to touch that. And after I distribute, I get negative 3n squared minus 15n plus 3 divided by n plus 5 times n minus 5. Now I look at that numerator and see it's a trinomial. I like factoring trinomials when they have a leading coefficient of positive 1, And I notice that I have a GCF of 3 here. But instead of just taking out a GCF of 3, I'm going to factor out a negative 3. And I'm left with n squared plus 5n minus 1. Because maybe that numerator will factor. Do any numbers multiply to negative 1 that add to 5? I don't know any numbers that do that, so that numerator cannot be factored. This is my final answer. Your answer is fine as long as it's equivalent to that. But if you didn't deal with that negative 1 back in the beginning, your final answer will have a common factor that it will cancel out. But because we dealt with that negative 1, we made our life a little bit easier. Number 3, we have a complex fraction here. Do not panic, because there's too many fractions going on here. Big picture, I have 5x plus 2, 5x divided by 2 plus 1, divided by 5x over 4 minus 1 over 5x. Let's make this first term one rational expression. The common denominator would be 2, so I'm going to have to multiply that 1 by 2 over 2. And I get 5x plus 2 divided by 2. That's equivalent to the numerator of that expression. Divided by, let's make this one fraction. What's my common denominator going to be? Well, I have a factor of 4, and I have a factor of 5x, so I'm going to need 20x in the denominator of all of these. This first term is missing a 5x. And the second term is missing a 4, so I need to multiply that by 4 over 4. Well, 5x plus 2 divided by 2, divided by, not plus, divided by, that gives me 25x squared. Now they have a common denominator, so I can write it as one fraction, minus 4, divided by 20x. Now this looks like something we did yesterday. I have two rational expressions and I'm dividing them, so I'm going to multiply by the reciprocal. And hopefully you're looking at 25x squared minus 4 and saying, wait a minute, that's the difference of perfect squares. That's 5x minus 2 times 5x plus 2. And that 20x is left on the top. So I can simplify as long as there's a common factor in the numerator and the denominator. And both of these expressions have a factor of x plus 2. So we say goodbye to the 5x plus 2 because they divide to 1. I'm also looking, I have a factor of 20 and 2. Those divide out and leave behind a factor of 10 in the numerator. So my final answer is this expression is equivalent to, this original expression, and all of these expressions actually, are equivalent to 10x over 5x minus 2. That is our final answer. Another complex fraction. Remember, we don't need to panic, we just need to remember complex fractions are just division. So I have 1 plus 4x plus 3 divided by x squared plus 1 divided by 1 minus x plus 7 divided by x squared plus 1. Let's deal with the first rational expression. I need a common denominator of x squared plus 1. So I'm going to rewrite that 1 where I can multiply both the numerator and denominator by x squared plus 1. Plus 4x plus 3 divided by x squared plus 1. Divided by, let's see what I can do over here. Notice that it's subtraction. So I don't make any mistakes, I'm going to make it an addition question and move that negative 1 into the numerator. Just so I don't lose that negative and I don't forget to distribute, I'm going to make that subtraction question an addition question by distributing that negative 1 in. Over here, I have x squared plus 4x plus 4 divided by x squared plus 1 divided by Well, 1 is really x squared plus 1 over x squared plus 1 plus negative x minus 7 divided by x squared plus 1. So now that I finally wrote this as one fraction, I can finally make this division question a multiplication question. I can write this as one big fraction with the denominator of x squared plus 1, but because it's division, I have to flip it, and that x squared plus 1 is going to end up in the numerator. And left in the denominator, I have x squared plus 1, x squared minus x, 1 plus negative 7 is negative 6. So, to multiply these two rational expressions, I just need to factor. How do I factor x squared plus 4x plus 4? Well, that's x plus 2 times x plus 2, because 2 times 2 is 4, and 2 plus 2 is 4. X squared plus 1 cannot factor. This is not the difference of perfect squares. X squared plus 1 does not factor over the real numbers, so I'm not going to touch that. This trinomial in the denominator over here, that factors into x minus 3, x plus 2. Are there any common factors in the top and the bottom? Well, there's a factor of x plus 2, and there's a factor of x plus 2. And then I also have a factor of x plus 1 and a factor of x plus 1. So let's say goodbye to those factors. Goodbye, goodbye. And we're left with x plus 2 divided by x minus 3. And that's that rational expression in simplest form. One thing that I've been careless doing this entire problem is putting equal to signs between each of my steps, because we need to remember that all of these expressions are equivalent to each other. We're just changing the way they look. We're not actually changing their value. They're all the same expression, they just look different. Number 5, explain why this rational expression, the sum of these two rational expressions, does not depend on the value of y. Well, let's add them together. So to add rational expressions, I need a common denominator. This has a 2y minus 6. This rational expression is 6 minus 2y. Those look awfully similar. And this is where that idea of negative 1 comes into play. I'm going to take that 6 minus 2y and factor out that negative 1 and be left with 2y minus 6. Now, I'm going to take that negative 1 and I'm going to throw it in the numerator just to make my life easier. 3y divided by 2y minus 6 plus minus 9 divided by 2y minus 6. They have a common denominator, so I can rewrite it as one expression, 3y plus negative 9, so 3y minus 9 over 2y minus 6. I'm going to take out a GCF because I see that. Maybe something will divide out. GCF of 2. This looks promising because there's a factor of y minus 3 in both the numerator and the denominator. So, goodbye, goodbye, and we're left with 3 over 2. Regardless of what value I plug in for y in this expression, I will always get 3 halves. You will always get 1.5 if you pick y equals 1,000,000, if you pick y equals 10. Notice that I can't pick y equals 3. That's going to come back to us tomorrow. Y cannot equal 3. If I pick 3, this expression's undefined. 3 is not in the domain of this expression. But I can pick any other number, and I'm always going to get 3 halves once I simplify it. So this does not depend on the value of y because it's always equivalent to 3 halves, and 3 halves clearly does not depend on the value of y. Finally, number 6, write this expression as a single fraction in simplest form. So this one's a little bit tricky because there's extra variables. We're used to working with one variable, so the factoring might be a little bit more difficult in this one, but we can do it. I see that it's a subtraction question, so right away I'm going to rewrite this subtraction question as an addition question by taking that negative 1 and putting it in the numerator. So now I need a common denominator. I notice that this has a factor of b minus c. So how does this denominator over here factor? Looking at that, I notice that I need b times b to get b squared. Once I factor that trinomial there. And I also need c times c to get c squared in that second c. And I need negative 2b once I negative 2bc once I add them together. So I'm going to try this and see if that works. Does b minus c times b minus c give me that expression? Does b minus c times b, well, that gives me b squared minus bc, so minus 2bc, that's good, plus c squared. This factorization does work, and this just gets used to that looking for and making use of structure of realizing that this is a perfect square trinomial where both of the factors are b minus c. Again, that was the most challenging part of this entire question. Plus negative b over b minus c. Well, this second rational expression needs another factor of b minus c, because I need two of them in the denominator. So I have b squared minus b squared plus bc, once I distribute that negative b, divided by b minus c times b minus c. Again, these are all equivalent. Now, b squared minus b squared is 0, so this gives me bc over b minus c times b minus c. Just don't start slashing things out. Do we have a common factor of b minus c in the top and bottom? No. Do we have a factor of b or c in the denominator? No. We just can't start slashing things out. So as a single fraction in simplest form, we have bc divided by b minus c times b minus c. Or, if you want it to be fancy, it's bc over b minus c squared. So this one was tricky. The hardest part was factoring that trinomial there. That was the hardest part of this question.